In this video, we'll look at center of mass. Before we do that, are center of mass and center of gravity the same? They are related, but they are not always the same. So let's have a breakdown of this. So what is center of mass? Center of mass is the weighted average of different masses of a body or an object. Or we can say is the point where the mass of an object is evenly distributed in all directions. So of course we can also say that it is the average location of all the mass in the system. So mathematically, the center of mass of a body or object can be evaluated using this formula, where mi is the mass of the ith particle, ri is the position vector of the ith particle. For a continuous object or body, the center of mass can be evaluated using this. So the only difference is that this summation sign changes to the integral sign. So we now see that the center of mass is a property of the object's mass distribution, and it doesn't depend on external forces like gravity, as we shall see in the center of gravity. So what is center of gravity now? Is that point where the total weight of the object is considered to act. You see, where the total weight of the object is considered to act, and it depends on the gravitational field acting on the object. So very important. Center of gravity depends on the gravitational field acting on the object, and it can be evaluated using this formula. Of course, in the absence of gravity, it approximates to what we have here, the formula for center of mass. So Gi is the gravitational acceleration at the location of the ith particle. So in a uniform gravitational field, we now notice that the center of gravity and center of mass coincide, but in non-uniform gravitational field, the center of gravity and center of mass may differ because of the gravitational force, which varies across objects. Now let us look at examples. For a uniform object, example a rectangular block on Earth, we see that the center of mass and center of gravity are the same because the gravitational field is uniform. But for a large object, let's say a space station in orbit, the center of mass remains fixed, but we see that the center of gravity may shift due to variations in gravity. Where are these concepts applied? For instance, in mechanics, in calculating the motion of objects, we see that center of mass is helpful, again, in designing stable structures and vehicles. And for center of gravity, we see that in engineering and architecture, where stability of bodies are usually taken into consideration. Another one is in aerospace, where it is used to balance aircraft and spacecraft. So if you have perform an experiment involving meter rule, you notice that the center of gravity is usually found at that point where the knife edge balances the meter rule. Then if you add different weights at different sides of the meter rule, you now see that the center of gravity, now the center of mass, tends to lie at that side that is closer to the object, or to the object with higher mass. So these are objects center of gravity. You see, this is at the diagonal, the center of the diagonal of this. This is a rectangle. So this is a circle. We can say it's a circle. So this is a cone. This is a triangle. So this is, let's say this is a cylindrical rod. So for a very small object, we see that the center of mass and center of gravity appears to be the same. So now let us look at position of center of mass along x-axis. So we call it, in this case now, position of center of mass in one dimension. So we look at two masses lying horizontally along the x-axis. So if we are to draw this is the first mass, this is the second mass. If we are to draw a line to pass through this and label the axis, let's say this is the y-axis and this is the x-axis. From this side is positive x, of course this is positive x, and this is a positive y. Now we can find the position of this center of mass of these two bodies. So how do we find the position? Of course, we know that the position of this object center of mass will lie closer to the object that has the greater mass. So if x1 now is the distance from this midpoint of this object to the origin, we take this as the origin 0, and x2 is the distance of this body m2 from this origin again, we can find the position of the center of mass, which is xcm. We denoted it with xcm because this is along the x axis. It can also be along the y axis. So if it is along the y axis and x axis, of course you are now looking at position of center of mass in 2 dimensions, where your center of mass will now be it will now carry both x component and what y component. So that is position of center of mass in 2 dimensions. We are only looking at the position of center of mass here along the x direction. So it is gotten using this formula. This is xcm equals the mass of the first body times this is x1, which is the position of that body from this origin, plus the mass of the second body times the position of this second body from the origin upon the total mass. This is just like the weighted average of the masses. So we can write this as a summation. So we can say that xcm is the sum of, if we take, of course this can be up to 3, can be up to 4, then we can say summation from I equals to 1 to a number which we don't know. It can be 10. Of course the masses can be 10, it can be 3, so 1 to, let's say, n. Then we now have mi, then we have xi. So this means in this case now what we have just have is m1 x1 plus m2 x2. So it now means that n here in this case is what? 2. N in this case is 2. Starting from 1, we have 2 masses. Then upon, this is the summation of the masses. Summation of the masses, m. So mi. So we can say I starting from 1 to n. Or we can just write it as summation of m I x I. Then this is I from 1 to n upon capital M. This capital M is the total mass, the addition of the 2 masses. So this is the expression for finding the position of center of mass for bodies in 1 dimension. If this is to be along the y-axis, it will be ycm equals, you have I to n, you have mi yi upon capital M. So this is how to, the formula to find the position of center of mass in 1 dimension. Now let us look at an example problem. Before we look at an example problem, if this is your first time of watching our videos and you like it, give it a like and share it with your friends. So don't forget to subscribe for more updates like this. We upload videos in sciences and technology. Now let us look at motion of center of mass. We look at motion of center of mass, then we now solve an example. Now if you watch this, this is along the x direction. So of course we can generally find the position vector of the center of mass. How do we do that? But before we look at that, so if this is the position vector r, the sum of the masses and the position vector, we can write it as this. So this is r is for the position. Of course, if this is two dimension, it will look like this. You have something like this. So this is let's say this is r. Now this is r. Of course, this is r y and this is r x, which we can call this is rj and this is ri, so that r, which is the magnitude, it will be ri plus rj. So if we want to find the sum of the masses and the position, so we can denote it as this, where r is the position vector. If we differentiate this, equation 3 with respect to time, we have this. But before we look at that, now look at this equation 1 and 2. Equation 1 and 2. This equation 1 and 2, this gives the velocity or acceleration of system's center of mass. Just following from what we did here, this is the position of the center of mass along the x-axis. So we can as well find the velocity or acceleration of system center of mass using this, and it is this that I want to show how this is gotten. So let's forge ahead. So we have something like this. If we differentiate this with respect to time, of course this is the r upon the t, which is an expression when you differentiate position with respect to time, that is velocity. Then this will be v1, this will be v2, and this will be vn. For a system of n particles, the linear momentum of the system is defined to be the vector sum of individual particles of the system. So if this is the case, we now see that we have this p equals p1 plus p2 up to pn. So the sum of the individual momentum gives the total momentum, which of course is logical. And if this is the case, if we compare equation 5 and 6, we see that p equals mv. This gives the relationship between mass and velocity, and this defines the linear momentum of an object. So we now see that the total momentum of a system of particles equals the product of the total mass in capital and the velocity of the center of mass. Of course, the velocity of the center of mass is what I have shown before. This is the velocity of the center of mass. This is the velocity of the center of mass. How is this even possible? Now let us go back to this derivation. So how do we get this velocity of center of mass? If you watch from equation 5, if we make v subject to the formula and we call it velocity of the center of mass, that is from this equation 5, we have something like this: m1v1 plus m2v2 plus we have this mn vn upon then capital M. And this is what we define as, this is the sum from I equals to 1 to n of MIVI upon capital M. This is what we have previously there. So this is what we have here. This is what we have here. This is the velocity of the system center of mass. The same thing applies with the acceleration. For instance, now, if we differentiate this equation 5, this is equation 5 with respect to time, of course we have this. It gives expression for the Newton's second law of motion. Of course, we now notice that if we make A subject of the formula, we are finding the acceleration of the system's center of mass, and we have something like this. We have that ACM equals, this is summation from I equals 1 to n. This is, you can say this is MI AI upon capital M, and this is what we have here. That is what we have here. This is what we have here. So this is the formula for finding the acceleration of the object's center of mass. So going further, we now see that this equation 9, the equation 9 states that the center of mass of the system of particles moves as if all the mass of the system was concentrated at the center of mass, and all the external forces were applied at that point. Now, let us solve a problem to illustrate what we've been saying. So, example, two masses of the Earth and Moon are separated these are the masses 5.98 times 10 to the power of 24 kilogram and 7.35 times 10 to the power of 22 kilogram respectively. So, and their centers are separated by this. Where is the center of mass? So first of all, now we look at the bodies. You see, this is Earth's part, the mass. This is 10 to the power of 24. This is Moon, 10 to the power of 22. We see that the center of mass will lie closer to this mass, which is the mass of the Earth. So first of all, draw. We can take this as the Earth and take this as the Moon. Then we'll draw a line to pass through the center. Of course, let's consider this to be the X direction. So, and the distance between the two centers is 3.84 times 10 to the power of 8 meters. So this is the distance. So let XE be the position of the center of mass along this direction, and XM be the position of the center of mass along this direction, center of mass of the Moon. So how do we now find the position of the center of mass? So we can call it, let's say this is, we'll say it will lie closer to here. Let's say that this is XCM. So we need to find an axis where we take our point. So we can say let this place be let this be y axis. Of course, this is y axis, and let this place be what? X axis. So let's take that this is origin. This is the origin. Okay, such that the position of the center of mass of the Earth from this point is 0. So we see that if this is the origin, the position here will be 0, and the position of the center of mass from this point to this point will be 3.84. 0.84 times 10 to the power 8. So utilizing this formula now, of course, the two masses we have here is the Earth and the Moon. So the formula we had before is that XEM equals M1 X1 plus M2 X2 upon the total mass M1 plus M2. So in this case, what we are considering is the Earth and the Moon. So the Earth, the first mass will now bear Earth. The first position will bear, this is the position of the Earth. So plus the second mass will be the mass of the Moon. The x2 will be the position of the Moon from this axis. Of course, this is the axis we chose as far as this question is concerned. So if we now consider the mass of the Earth, we now see is 5.98 times 10 to the power of 24 kg. So we write it. So the position of the center of mass of the Earth is 0. If we take this as 0, this point as 0, so this is 0, plus the mass of the Moon is 7.35 times 10 to the power of 22, and the position of this center of mass of the Moon from this origin is 3.84 times 10 to the power of 8 meters. So we have is this. So upon the mass of the Earth, as we know, is this, plus the mass of the Moon is this. So once you do this calculation, you have that the position of the center of mass of these two bodies along this direction, x-axis, is 4.6624 times 10 to the power of 6 meters. And you now notice that this is within the radius of Earth, which is about this this distance. This is 6.4 times 10 to the power of 6 meters. In our next video, we'll look at the position of center of mass in 2 dimensions, specifically in IJK unit. So if you have enjoyed this video, give it a like, subscribe for more updates so that if we post our video, you'll see it, and share it with your learning colleagues or anyone who might find it very helpful. Thank you and have a wonderful day.